This video is about section 2.3 from your textbook. At the end of this video, you should be able to define energy and work and talk about the different types of energy that we know to exist. Tell me what a chemical reaction is and what we're symbolizing when we write out chemical equations. Be able to tell the differences between the three fundamental types of chemical equations. Identify the things that make a chemical reaction happen faster or slower, and define metabolism. Very generally speaking, energy is the capacity to do work. It means moving something. Everything that our bodies do, whether it's intentional or automatic, is a form of work. Potential energy is the energy that is stored in something, usually because of its position, but it is not doing work at the moment. I used to tell my foster daughter, she used to like to climb trees, that when she got too high, she had too much potential energy. So we can think of water behind a dam. If the dam were to break, there is potential for huge devastation. But as long as the water is just behind the dam, its potential energy is stored there. Kinetic energy is what happens when the potential energy is set in motion. So my foster daughter climbing the tree too high, if she were to fall and her potential energy was converted to chemical energy and then to mechanical energy when she hit the ground, those are three different types of energy depicted in one unfortunate event. Kinetic energy is also heat. So when something is warmer, the molecules within it are either moving or vibrating faster than when something is cooler. So we have kinetic energy going on at the molecular level. And electromagnetic radiation, for instance, the microwave that maybe cooked your lunch today, that is a form of kinetic energy because the photons of radiation, the little discrete packets of radiation, are moving. They have kinetic energy. So now we're moving on to chemical reactions. Generally speaking, a chemical reaction is anything that forms or breaks chemical bonds. When we write a chemical reaction, we have the reactants, or the starting point, on the left, and then the product, or the end point, on the right. Our three general types are decomposition reactions, synthesis reaction, and exchange reactions. And we're going to talk about each one of those coming up. So when I taught high school chemistry, the analogy that worked really well for describing these types of reactions and classifying these types of reactions is to think about dancers. Okay, so here in my reactants at my start, I have a couple dancing. A is dancing with B, and then the reaction happens, and then they're separated. Maybe they had a fight or something. So that's a decomposition reaction. The pieces are coming apart. A synthesis reaction is just the opposite. I have A and B as reactants. They are uncombined. They're separate from each other. And then at the end of the reaction, they are chemically combined. In an exchange reaction, we have a couple dancing, A and B, and a different couple dancing, A and B. And then there's this intermediate step where everybody is kind of all glommed together. And then at the end of the reaction, A is dancing with C and B is dancing with D. Our two couples swapped. Okay, so decomposition reactions. Something is breaking apart during the reaction. Synthesis reactions, something is being built from the component pieces. And an exchange reaction, the two reactants swap places, and we end up with two different substances at the end of the reaction. So a decomposition reaction where we have something complex broken down into individual pieces. A starch molecule, maybe you find this in wheat or potatoes, broken down into individual glucose molecules that can fuel the reactions in your cells. Here we have a synthesis reaction. We have individual amino acids that are going to get joined together into a more complex protein molecule. And an exchange reaction, remember we have A and B and C and D. We form this intermediate that is only there very, very briefly, and then at the end, A and C are joined together and B and D are joined together in the exchange reaction. Oftentimes, reactions are reversible. Depending on the circumstances, we can go one way or another way, and we show this by double arrows. Okay, so let's imagine a scenario. We have a patient who has a high amount of carbonic acid in the blood. So this can happen when a person experiences hypoxia. They aren't getting enough oxygen. If a person hyperventilates. Remember I told you in a video a couple back that we don't want to change the pH of our blood. Small changes in the pH of our blood lead to pretty devastating disease outcomes. Okay, so we're having acidic tendencies in the blood with this carbonic acid buildup. So your body has two ways of dealing with that. The first way is to produce bicarbonate, and this would get excreted in the urine. And the second way to deal with the carbonic acid would be to breathe out more carbon dioxide and water, which is what you're breathing out anyway. So this is an example of a reversible reaction. Equilibrium happens when the reactants and the products, or the reactants and the products, are all in stable quantities. No one is increasing or decreasing at the expense of another. Reactions happen only under specific conditions. First, the molecules have to physically bump into each other with enough force that the reaction can happen. And second, they have to be facing the right way for the reaction to happen. So we need molecules colliding with enough force, and we need them to be oriented or facing the correct way. There are three ways that we can increase the rate of a chemical reaction. The first thing is we can make the reactants, the starting things, more concentrated. So if there's more of something, it's more likely that by chance it's going to bump into the other reactant with the correct orientation, and the reaction is going to start happening. The second thing that we can do is we can increase the temperature, especially in a liquid. This means that the molecules are going to be moving faster and with more kinetic and mechanical energy. So as they move faster, they're more likely to bump into each other. Think about on the interstate. When people are driving faster, they're more likely to bump into each other. So increasing the temperature increases the kinetic energy of the molecules, and that will increase the force they have when they bump into each other and make it more likely that a reaction will occur. And the third thing, we're going to be talking about this more in a later video, but the third thing is that a catalyst is present. And in a biological system, the catalyst is referred to as an enzyme. It's a very special protein that does a very special job. And what a catalyst, specifically an enzyme catalyst, does is it holds the reactions in the right orientation so they're able to do their chemical reaction very efficiently. We'll be talking about this much more later. So finally, we're going to be talking about metabolism here. So all of the reactions in your body can be considered your metabolism. It's not just the breakdown of food, though that is a big component of it. So catabolism is the breaking of bonds, breaking something down into smaller pieces, and it releases energy. So when I eat a cheeseburger for lunch and all the bonds in the fats and the proteins and the carbohydrates in that cheeseburger get broken down, smaller food molecules are being built, individual amino acids, individual fatty acids. That's going to release the energy stored in the covalent bonds of the cheeseburger and allow my body to use that energy to maybe go for a run this afternoon. Anabolism is when we do a synthesis reaction and we build larger molecules, and this requires energy. So if after my run I decide to lift weights for a while, I'm building the muscles in my body, and muscles are made primarily of proteins. So this requires energy. I need to eat nutritious foods that can provide energy so that I can build my muscle mass. Catabolism and anabolism are very much linked. I can't build muscle mass unless my body is doing catabolism of my food. They go hand in hand.